All right, there are two AP Physics C exams, and apparently, because of the fact each one is only 90 minutes, we have to release two sets of each of those, and there's three free response questions for each one, which makes 12 problems I have to solve here, okay? Now, what I am going to say, I might split this into two videos, one for mechanics and one for EMAG, but I will say while I didn't rehearse this, I did flip through and look at the diagrams, mostly because I wanted to find out if these were any questions that I wrote. And I don't think a single one of them was any questions I wrote. So we're going to do sets 1 and 2. We're going to do them back to back, alternating between set 1 and set 2, because since both sets had the same multiple choice questions, they had to write two almost, but not quite identical questions, 1, 2, and 3, in order to make sure that they can score both sets using the same multiple choice and using the same like cut points and things. I bet you why. Okay, so let's look at what's going on here. All right, block A and block B, masses M and 3M. You can see that. Range is set up, ideal spring constant K, horizontal surface. Friction is negligible except in this region D, where the coefficient of kinetic friction between block A and the surface is mu. B is attached to a string of length L. This is symbolic because I'm not seeing any numbers, okay? All right, let's make sure you see the picture there. Okay, as shown in figure 1, block A is held against the spring, compressing the spring at distance x. C for compression, I'm assuming. Okay, we can see that there. All right. Oh, my gosh. Okay. Oh, so we're doing this now. Okay. Apparently, we're putting the command words or the task verbs in boldface now, starting this year. Okay. At time 0, block A is at x naught and is released from rest. After the block is released, the following occurs. Good grief. Okay. Time T1, block A is at x1 traveling at distance xc. Block A moves at speed v, and the spring is at its equilibrium position. Time T2, the left side block A is at x equals x2, passing through distance d across the region with non-negligible friction. So basically that means that the block is off the frictiony part then. And at time 3, block A is at x3 and collides. Oh, gosh, this is so much reading. Oh my gosh, it's like freaking reading War and Peace. Okay. The question is, what color pen am I going to use? I'll use green. I don't know if you can tell that that's green. Looks black there, but it's green. Okay. For parts A, I express your answer in terms of that G. Okay. Derive an expression for the speed v of block A at time T1. What is time T1? That is right when we get almost to the frictiony bit right there. So am I just going to say 1/2 K, what am I allowed to use here? XC squared. That's the spring's potential energy, becomes 1/2 mv squared. Okay, well, K over M, XC squared equals V squared. V equals radical K over M. XC is outside the radical because you take the square root of both sides. Driving expression of the speed V A B of the two block system immediately after the collision at time T3. Ha. All right. So I have to do both energy and momentum. So I'm going to say this. I'm going to say just before the collision, or I'm just going to say before the collision, we're going to have energy 1/2 kx squared is the potential energy, and then that's going to equal 1/2 mv initial before the collision. It's 1m, isn't it? Okay, and then plus some energy dissipated. So this energy dissipated is going to be the friction force times, how long was that distance, capital D? Okay, the friction force is mu mg, mu force normal, D. Okay, so now I'm going to solve this. 1/2 kx squared minus mu mgd is equal to 1/2 mv squared initial before the collision. Okay, so now we're going to cancel or multiply everybody by 2, divide everybody by m, and the v just before the collision, this sucks. Kxc squared over m minus 2 mu gd. That's before the collision. Now we have to do before the collision momentum equals after the collision momentum. So we're going to have mv initial equals 4m v finals because you go from 1m to 4m's. So that means that v final is going to be 1/4 of v initial. So that's going to be 1/4 of radical kxc squared over m minus 2 mu gd. D, capital D, capital D, capital D. Okay, to make sure you use the right case. All right, well, that sucked. On the following axes, sketch the graph of the kinetic energy K of block A as a function of time t from 0 to time 3. Okay, as a function of time, the kinetic energy is going to increase like this, and this is a piece of a sine square root of k over m times t from simple harmonic motion. That's 1/4 of a simple harmonic motion. Okay, now this is going to be a constant velocity, a constant acceleration. So during this segment, it's going to be v equals v naught minus at, constant acceleration. So the kinetic energy is 1/2 m and then v naught minus at squared. So this is going to be a parabola, and the parabola is going to actually look like this. The parabola, I think, is going to look like that. Now, why am I saying that? Here, let me give you another reason. The work done by friction is friction force times distance, and that's a constant. But at the beginning, you're going to cover more distance in the same time than at the end. So because you spend more distance going fast, you lose more kinetic energy because you have a lot of distance at the beginning, less at the end. Then this is going to be flat because it's friction free. And then it doesn't say, I need to stop now, but the kinetic energy will drop substantially once the collision happens, but you don't have to put that. All right. Using principles of work and energy, justify the graph drawn in part BI from the interval t equals 0 to t equals t1. Explicitly reference features of the shape of the graph you drew in part BI. I guess maybe I'll say this. I might say work is like, I don't know. I just want to say force times distance. And I want to say that there's more force at the beginning, if I can spell that word correctly. So beginning, I can't spell anything today. All right, so there's more force at the beginning because the spring is compressed more, because F equals KX is more or something like that, right? Okay, so what do I want to say then? I want to say, so you're going to gain more kinetic energy at the start. So there's a steeper slope, okay? And then I might say, as the spring reaches equilibrium, okay, as the spring reaches equilibrium, F equals KX is less. You do less work per time or something like that. I don't know. All right. Oh, what are we still going here? All right. After the collision, two-block system instantaneously comes rest time T4, which occurs when the string makes a small angle with the vertical. That tells me we're about to do a pendulum. With the vertical, for times greater than T4, the system oscillates with frequency F. The support holding the string is raised, and the procedure is then repeated at a new string length 2L. How will the new frequency? Okay, period equals 2 pi radical L over G, and that's 1 over F. So a longer length will be a longer period and a lower frequency. So the frequency is lower, and I'm basically going to write about this. I'm going to say longer length, longer period, and since frequency is 1 over period, right, period is 2 pi radical L over G for that piece right there. So more period, less frequency. All right, okay, one down, 12 to go. Where's the freaking one here? Okay, so what's going on this one? Okay, we're going to go down a hill with some mu and hit this shit. Okay. Blocks A and B, 2M and M, setup, ramp, angle theta, smooth horizontal table, ideal spring. Block A is held a distance, at rest distance D up the ramp. B is at rest on the horizontal table. Friction is mu in the region of length D, and there's no friction between the blocks and smooth table. Okay, so let's see what's going on here. Okay. Oh, we got another bulleted list. Dang, this is so much reading. At time 0, block A is 0. T1, the block, has traveled the distance D down the ramp, has transitioned to the table, and is moving speed V at time X1. At time T2, block A is collides and sticks. Time T3, the combined blocks are where they collide with and stick to the spring. I'm assuming the spring has no mass of its own. The combined blocks are instantaneously at rest, springs compressed. Okay. Derive an expression for V of block A at time T1. Okay. There's probably a couple of ways you could do it. You could do it with energy. And so energy would look something like this. You'd have mgh becomes 1 half mv squared and energy dissipated. The h would be d sine theta. So mgd, was that capital D? Yeah, d sine theta equals 1 half mv squared. And then energy dissipated would be friction force times distance, which is mu force normal times distance, capital D, which will be mu mg cosine theta times distance. So now the m cancels out. I'm going to bring this over. So it's mgd sine theta minus mu mgd cosine theta equals 1 half mv squared. No m, no m, no m. Factor, so 2g, because we're bringing that over. D sine theta minus mu cosine theta equals v squared, so you can take the square root. Now, that's one way to do it. The other way to do it is with Newton's second law, where you're going to say the downhill force minus friction equals ma. The downhill force is minus mu. Okay, we did it right here. Friction is mu normal is mu mg cosine theta, so I'm not going to do that work again. And then the mass cancels out. Great. All right. G sine theta minus mu cosine theta is equal to A. And now I'm going to use V squared equals 2A distance. So V squared is equal to 2. The A is G. And then I'm going to put the D here, and it is just sine theta minus mu cosine theta. And then you're just going to scratch that out, take the square root. Okay. Derive an expression of the spring constant. The spring, I really don't want to. Okay. So here's what's going to happen. We need to do the collision, which is, I'm going to call this V initial now. 2M, V initial is going to equal 3M, V final. Why? Because the 2M's are going to collide with the 1M. All right. And then the springy stretch is going to be energy. So here's momentum and here's energy. It's going to be 1 half 3M's times V final squared becomes 1 half K x c squared. The 1 halves can cancel out. Okay, so the V final is going to be 2/3 the V initial. So that's going to be 2/3 of radical 2GD sine theta minus mu cosine theta. Okay, does that make sense? Okay, now over here, we're going to say 3M times this squared. 4, 9, 2GD sine theta minus mu cosine theta is equal to K xc squared. Okay, now, I don't, do I, okay, so I got 8 GD over 3 sine theta minus mu cosine theta. And then we're just going to put the xc squared in the denominator, and then you can take K. Okay, I don't know if I did that right. Whatever. Oh, on the following axis, sketch a graph of magnitude and momentum. Momentum, huh? Is that what you want? Okay, the momentum is going to be a straight line here. The reason why is because the slope of momentum versus time is net force, and the net force is a constant on the incline. Why? Because the mg sine theta doesn't change, and the mu mg cosine theta friction also does not change. So they ain't going to change. From T1 to T2, no net force. From block A is going to lose some momentum. I think he has to give 1/3 of his momentum to little m. Okay, so at time t2, he's going to lose some momentum. And then when we hit the spring, delta momentum is force delta time. And at the beginning, there's not a lot of force, so we're going to lose momentum gradually. But later, there's a lot of force, so we're going to lose mass much more abruptly. That's a piece of a sine wave, is what that is. All right, from T3 to T4, it's exactly what I just said. Delta momentum equals F delta time for the first little delta time. F equals Kx is a weak force. So the slope of momentum versus time is not steep, right? As the force gets stronger, the slope becomes steeper. Okay, that's my opinion, and I'm sticking to it. Now, let's get the lights turned back on in here. Okay. Man, you don't move at all. They think that they're going to save some electricity. What is this? For times greater than 4, the two-block system oscillates with a period TO. Okay. The procedure is then repeated using a new ramp where there's negligible friction. The new period will be the same. Why? Because it's going to be the same mass of 3m. It's the same spring, which is K. Period is 2 pi radical m over K. So it's the same period. The only thing that would be different would be the amplitude would be greater because you have more energy. You didn't dissipate any energy. Okay. Is this set 1 again? All right. We're going to drop a cylinder. You probably better roll it so it doesn't tumble over, but then you get a Magnuson effect. Okay. Drag. Yeah, okay. Here we go. Student drops cylinder from rest. Air exerts a force drag. It's going to be BV squared, which means I'm not actually going to take an integral today because I don't know how to do BV squared, only constant times V. Although that is the true drag force, is a number times V squared. Derive, but do not solve. Derive. Can I just say right? Right? Drive. Drive, but don't solve. That's okay. Differential equation could be used to determine the speed V of the cylinder as a function of time t. All right, so you're just going to start Newton's second law is what you're going to do. All right, so you got an mg, the acceleration's down. You've got an F drag. So we're going to do mg minus drag equals ma. And so I'm going to say mg minus bv squared is m, and the derivative that makes it a differential equation is dv dt. So that's pretty much it right there. Okay. What's going on here? The student correctly sketches, yep, they did, v as a function of time. Draw a vertical line on sketch in figure 2 to indicate the earliest time at which drag on the cylinder is equal to the magnitude of the weight of the cylinder. I mean, technically never, guys, because it's an asymptote. So, here, that looks like when you reach Vmax, T1. Okay, well, I'm going to say this. The V versus time graph, it has 0 slope after time equals T1. Okay, so 0 slope, 0 acceleration, right? Okay, so the two forces, mg and F drag, must balance and equal. Is this what you want to hear? I mean, I don't know. I didn't make this question. I would never have done something like that. Okay, rather than dropping the cylinder from rest, the student throws the cylinder upward with a non-zero initial speed. The cylinder is in the same orientation. The student allows the cylinder to fall to the ground. Indicate whether the magnitude of the cylinder's maximum downward speed after being thrown upward would be greater than maximum downward speed would be the same, equal to. Briefly justify your answer. Okay. Well, when V equals V max, the sum of all forces is 0, and B V max squared equals mg. B, M, and G did not change. So Vmax is the same. All right, it'd be the same. By the way, can I just tell you what it would look like? Here's what it would look like, okay? This is downward velocity. And then on the other side, this would be upward velocity. I know that's confusing that down is up and up is down. But then you would actually have something that looks like this. So it would very rapidly quit going up and then start going down, but only reach a maximum speed there. That's what would happen there. Oh, this is an experimental design question. Where's my straight edge? Okay, the student conducts experiment to better understand the relationship between Vmax and mass. The student collects data, graphs Vmax squared versus mass, draw a best fit line, which means draw a line that goes near all the data points and has at least one above and one below. Can you see that nice purple? That's a nice purple. Okay. Use the best fit line to calculate experimental value for B. Okay. So I'm going to say this. BV squared equals mg. So here I've got V squared and M. So the V squared is my rise and the M is my run. So on the other side, we have to have G over B, and that's the slope. So I'm going to select 2 points from the graph. What is that? That's what's the average of point? Oh, wait a minute. This is one. What? That's maybe 0.75. Okay, so this is 0 and 0.75, and then over here, I try to choose points that are far apart. Okay, what is that? 0.55. Okay, and 0.55 and 9.5. Okay, so then I'm going to do 9. Shut up. Come on. 9.5 minus, what was that again? 0.75 over 0.55 minus 0. Okay, so I'm going to write that out. I'm going to say the slope is 9.5 minus 0.75 over 0.55 minus 0, which is 15.91. That's equal to G over B. So B is going to equal G over 15.91, right? And so 9.8 divided by 15.91 is going to be a B of 0.6159 or maybe 0.616. And I'll bet you I need to put units on this because it says calculate. So what would the units of this be? This would be B times meters squared over seconds squared equals kilograms times meters per second squared. No, almost. So this would be kilograms per meter. Yeah, it's kilograms per meter. I didn't make this up. It's not my fault, okay? All right, here's what I'm going to do really quickly is I'm just going to make a little graph of, let's say, y equals 0.616 over, 9.8 over 0.616. Okay, I'm just going to do this really quickly. And then on my table, I'm going to put 0.1, 0.2, 0.3. Oh, I forgot to put the x. It'd be nice to put y equals slope times x, wouldn't it? Okay, and then as I look, I'm kind of seeing the same numbers about that I got here. Okay, so I'm just double checking that this seems reasonable if I plug it back in and do it again. All right. Oh, there's even more to it. Okay. A student claims the maximum speed of the cylinder drop from rest depends on the length of the cylinder. The student designs the experiment to collect data. It can be used to provide evidence to support the claim. The student drives cylinders for orientation. The student has access to, but does not have to use all the following equipment. Cylinder set 1, same known length and different known masses. Cylinder set 2, the same known mass but different known lengths. A motion detector that can measure velocity as a function of time. Indicate 2 quantities that, when graphed, could be used to determine whether the length of the cylinder affects the maximum speed. Okay, it does not say what type of relationship. So I think I'm just going to say V versus L. Describe how the quantities graphed could be used to determine the relationship between cylinder length and maximum speed. So you're going to graph the maximum speed V on the vertical, and then maybe L on the horizontal using cylinder set 2. Okay. To determine the relationship. I mean, what do you want me to say, right? This is what my students would do. What my students would do is to perform a power regression y equals a x to the b of the v versus L data, right? And look at b, the exponent to determine the type of relationship. So we do this a lot in my classroom. We do this in P1 a lot and also in C, where the students don't know what the relationship is. So what they're going to do is they're going to try different L's, measure different V's, and then they're going to look at the exponent. And what my students are trained to do is to look for the numbers 0, positive or negative 1/2 for the exponent, right? Positive 1, negative 1, positive 2, and negative 2. And so we call this no relationship at all. So if they get an exponent at 0, there's no relationship between the two. This I call a root relationship, and I call this an inverse root. And an example of that would be period equals 2 pi radical L over G. Period and L have a root relationship, but period and G have an inverse root relationship. This is a directly proportional. This is an inversely proportional, right? So, in the equation PV equals nRT, P and T have a direct proportion, but P and V have an inverse proportion. And then I call this a quadratic, and then this is an inverse square, right? So inverse square would be like force and distance in Newton's law of universal gravitation. Quadratic would just be x versus t for a constant acceleration. So I don't know what they really wanted there. All right, I just didn't know. I don't think they know what they want. Okay. A student drops a sphere mass m from rest. Air exerts a drag force, a magnitude F drag on the sphere. The student models the magnitude of the drag force as BV. Okay, great. Okay, right, but do not solve. So once again, it's going to be mg. Mg minus force drag equals ma. Mg minus BV equals m dv dt. Okay, we did that. All right, so what do we got going on here? Hey, vertical line. All right. The earliest possible time at which F drag is equal to the weight, so it's the exact same story. I would probably put it right here. TT, Y, I said Y before. I'm not going to say it again. So go back to set 1 and see what I said there. The velocity has 0 slope, so the acceleration is 0. Suppose the student throws the same sphere downward. Oh, they're going to throw it downward with non-zero initial speed. The magnitude of the new drag force at terminal speed is F nu. F nu would be the same. All that happens when you throw it downwards is this is now time equals 0 because you already have, I didn't look at this. This is the force of drag versus time, not the velocity versus time. Okay, so okay, now I actually am going to justify this. I'm still correct here, as I'm going to say here. But what I'm going to say here is I'm going to say when the F drag equals mg, the velocity cannot increase anymore. That's Newton's first law, right? But since drag equals bv, if v can't increase, F drag can't either and is constant. Okay, so once again, the drag force is going to be equal to, regardless of throwing it down. The reason why is because the drag force is equal to mg at maximum speed and maximum drag, right? And we did not change M or G. We did not change M or G. Okay. All right. Okay. Let's just calculate. I'm not even reading this. I'm just going to calculate the slope straight off. All right. So this is 25. The slope is going to be 25 minus 0. Okay. And then what's this number? 16, 17, 18. Okay, so that's 18 minus 1. So that's 17 over 25. I don't know what that is. 0.68. So the slope is 0.68. Okay, now let's read what's actually going on. Student conducts an experiment to better understand the relationship between drag and V. Okay. Use the best fit line to calculate the experiment. Well, the F drag is BV. Y equals slope X. So this is the drag code. That is B. B is 0.68. Oh my gosh. Newtons equals B times meters per second. Newton seconds per meter. Okay. That's if you solve that, right? So the B is the slope. All right. I feel like I should be insulted. All right. I was even more insulted earlier today. I did AP pre-calculus. That was not a difficult exam. Okay. A uniform rod of length L and mass M is attached to a pivot on a vertical pole. Okay. No friction between the rod and the pivot. Great. Horizontal string connects point Q on the rod and the pole. The rod makes an angle theta with the pole. Yeah, it's just what's happening there. On the following representation of the rod, draw and label the forces, not components, that are exerted on. Okay, so this is going to be 3 mg. His own mass is m, so he has an mg. He's going to have a force tension. And the pivot, I believe, needs to exert some rightward component of force to balance the left. And if I look at the torques acting around Q, which I'm allowed to do, I have two counterclockwise torques, so I need a clockwise torque. So I'm going to say that the F pivot is both to the left, to the right, and up to balance the torques, and to the right to balance the leftward force. All right. Figure 1. Point P is located 3/8 of the length from pivot, and point Q is 6/8. Derive an equation for the tension force. Okay. Okay, so this is 3/8. Did they seriously say 6/8? Like they didn't even reduce that. Okay. Okay, so I have two about the pivot clockwise torques and one counterclockwise torque. Okay, if this is theta, then this is theta, and this is theta, and I'm going to call this phi, which is the complement of theta. So what I'm going to have is I'm going to have a 3 mg acting at a distance of 3/8 L. 3/8 L times the sine of theta. And then we're going to have the 1 mg acting at 4/8. I mean, why not? When in Rome, don't reduce fucking fractions. Mg times 4/8 L times sine of theta. And then balancing on the other side is going to be tension acting at 6/8. Tension, force tension, acting at 6/8 of the length, sine of phi. Now, because theta and phi are complements, because theta and phi are complements, the sine of theta is equal to the cosine of phi, and also the L in every term cancels out. L is in every term. The 8 in every term cancels out, so this is going to become 9 mg sine theta plus 4 mg sine theta equals 6 ft, the cosine of theta. These are like terms. 13 mg sine theta equals 6 ft cosine theta. So tension should be 13 over 6 mg, and then you can say sine over cosine, or you can say tangent of theta. Okay, the original string is replaced with a longer string. Connects point 2 to a higher location on the vertical pole. The angle theta remains the same. Oh my gosh. How does the new tension compared to the original tension, oh, you might have gotten Mr. Friendly good. Okay, no, I take it back. Okay, so here's what I'm going to say. What I'm going to say is I'm going to say that the clockwise torques, which is from these two forces, equals a counterclockwise torque, which is from this one. Now, this is the same. All right. Light's still going off. Okay, so this is the same. These two counterclockwise torques are the same. But clockwise torques about this pivot are the same. That's the same. But this is going to be the same R times the force tension. And now it's going to be not phi, but a bigger angle times the sine of a bigger angle. Okay, so I'm going to say the clockwise torques equals a counterclockwise torques. The clockwise torques are the same. So the counterclockwise torque must be the same, which is RF sine theta. The R is the same. The theta is closer to 90. So sine theta is more. So the force tension is less than before. All right, so the new tension is less. Is this ever going to end? Okay, a non-uniform rod is now attached to the pivot. Shown in figure 3, there's negligible friction between that, and then the rod has a length 1.2 meters and a linear mass density that. Calculate the mass of the rod. Okay, so lambda is d mass, d length. So then that means that dm is lambda d length. The total mass is the integral of all these little masses. So then I'm going to divide and multiply by dx, making m equals the integral of lambda dx, which is the integral of a plus b. You gave me numbers. 6 plus 10x dx. And if I want the total mass of the rod, we're going to go from 0 to 1.2. Okay, so I got a calculator. What? I'm not going to do this. What the frick was that? Okay, let's, function numerical integration. 0 to 1.2. What is the freaking function? X dx. Okay, 14.4 kilograms. Calculate the rotational inertia. Now, rotational inertia is integral r squared dm. But the r is actually x squared, and we're actually going to say dm over dx times dx. That's lambda dx. So this is going to be the integral from 0 to 1.2 of x squared times 6 plus 10x dx. Yeah, you think I'm going to do that? I don't have to do this on the calculator. I just have to set it up. This is physics. This isn't calculus. X squared, parentheses, this bullshit, 8.64 kilogram meters squared. All right, that's the end of set 1. To the trash with you. Okay, what's with set 2? Okay, it looks like something similar. The uniform disc, radius r, mass md, is attached to vertical pole. Friction between the axle and disc is negligible. A lump of clay is attached to the edge of the disc. The size of the lump of clay is small compared to everything else. A horizontal string is connected from the pole to the edge of the disc at point A. String makes but the mass of the clay is going to be important. Okay. Angle theta. On the following representation, draw it and label external forces exerted on the system. All right. Well, mass of disc times G, mass of clay times G. There's the string, so force tension. And then now I have to think about the axis force. So once again, the axis is going to want to push up to cancel out these down forces, and the axis is going to want to push right to cancel out left force. So there's your Faxis right there, okay? All right, that's my story, and I'm sticking to it. Derive an expression for the tension of the string when the clay is at point A. Okay. So if I look at this axis, then the Faxis and the MDG, whatever, produce no torque. But these two guys are going to produce torque. And so it's going to look something like this. Where was the theta measured from again? All right, so here is force tension. Here's theta. Here's mg. This is phi, the complement of theta. Okay, so I'm going to say the clockwise torques balance the counterclockwise torques because this is at rest and equilibrium and all that stuff. Okay, and then this is R. So the clockwise torque is provided by mg, and it's going to be mg times R times the sine of phi, and the counterclockwise torque is R times tension, and that's going to be the sine of theta. And remember what we said, the sine of phi, because they're complements, really the cosine of theta, because they're complements, and the R's are going to cancel out. So what am I solving for? F tension. So there's going to mg cosine divided by sine, or mg cotangent of theta is equal to force tension. Do I believe that? Okay, here's why does this make sense? Okay, if the dot was right here, then no amount of tension could prevent this from rotating. And so at theta equals 0, I should get infinity, which is, cotangent of 0 is infinity. Okay, just making sure. All right, undefined. The string remains connected to the edge of the disc at point A. Okay, the clay is moved to point B. How does the new tension? It's got to be greater. So the new force tension is greater. Here's why. Because now the clockwise torque from the clay's mg equals the R tension sine theta. It's the same R, it's the same theta, but the clockwise torque is greater. Why is the clockwise torque greater? Because that is now a torque of R times mass of clay G times the sine of 90, which is greater. So then, if this is the same and the same, and this is greater, then the tension has to be greater. If I had time and space, I would write that. Oh, why? Why? A non-uniform disc is now attached to the axle. The lump of clay is attached to the disc at point B. The clay has this mass, and the disc has a radius that. The mass density of the disc varies radially and can be modeled as rho equals beta R, where R is the radial distance from the axle and beta is 4 kilograms per meter cubed. So if this is kilograms per meter cubed, and this is meters, then this would be kilograms per meter squared. All right. So calculate the rotational inertia of the disc, not the clay, but the disc. Okay, so here's what I'm going to say. I'm going to say I is integral R squared d mass. And now rho is d mass d area. So I'm going to do d mass d area times d area. I don't like this at all. Okay, and so this is going to become the integral of R squared times this, which is rho, beta R. And then what's the d area? Well, the area So, I mean, that's what that says. That says kilograms per meters cubed. So this has to be a d area. So what do you want me to say? Do you want me to say the area of a circle is pi r squared? So the d area is 2 pi r dr? Is that what I'm supposed to do? Am I supposed to say d area is 2 pi r dr? I don't know if I like that. I think I do like that. I think I'm going to go with it. Okay, so we're going to integrate from 0 to 0.3. 0 to 0.3, all right? It's going to be, okay, so this is the 2 and the pi and the beta are going to come out. The beta is 4. So the 2, the pi, and the beta come out, and I get r to the 4th from 0 to 0.3, which is now going to be, this is 8 pi, raise up the power to 5, divide by the new power, 5, and then this will be 0.3 raised to the 5th power. Okay, so let's see, what is 8 pi over 5 times 0.3 raised to the 5th? Okay, now let's see what happens if I functionally numerically integrate this. 0.3, is that what we got there? Okay. Inside the parentheses, it's going to be 8 pi over 5 times, oh, I didn't mean that. I meant just 8 pi times x to the 4th. It's the same number, okay? So then what am I going to get? I'm going to have 0.0122 kilogram meters squared. I'm making sure this sounds right to me. I'm sorry to take up your time, but this is, all right, let me just check my units. Can I? All right, this is kilogram per meters cubed. This is meters squared. This is meters. This is meters. This is meters. So yeah, kilograms meters squared. Okay. The string connecting the disk to the pole is cut. Calculate the magnitude of the initial angular acceleration of the clay disk system. Okay, so for this, what I'm going to say is I'm going to say the total rotational inertia is the eye of the disk plus the eye of the clay. So that's going to be 0.0122 plus the eye of the clay, which is just going to be m r squared, 1 mr squared. All right. So what's 0.6 times 0.3 squared? Okay, it's that. Plus this will be 0.0662. Sorry, you're not seeing this. That's the I total, kilogram meters squared. Okay, now I want to do torque equals I alpha. The torque is going to be due to the weight of the clay. So it's going to be mg times r. The angle between the r and that is 90 degrees, so forget that. Equals I total alpha. So then we're going to take the m. Oh, yeah, the m of the clay. The g, it's going to be ugly numbers anyway, so I'm going to use 9.8. 0.3 equals 0.0662 kilogram meters squared times alpha. So let us take 0.6 g radius divided by this, and your initial alpha is 26.64 radians per second squared. Okay. That sucked.